Okay, so let's number 1. This is number 3. So here is Fermi, and he was born in Rome, and when the time came to go to the university, he decided to go to Pisa, Scuola Normale, which was one of the best at the time. And that's where he met Rossetti, who became, one of his friends.
Your microphone is not working. Yeah, your mic's not working. I mean, you are technology.
So at Rome, they had this institute where they were working was the Via Panisperna was the physics department at the time, and a number of very enthusiastic and hardworking physicists got together. And what you see here is D'Agostino, Segre, Amaldi, Rossetti, and Fermi. And often then they had, later on, they had Majorana and Pontecorvo joining them. And these had other 2 giants of physics. Still now, people are looking for a particle that Majorana said at that time would have been discovered sometime. There's still many experiments which look for the Majorana neutrino. So you see how, Fermi was called the Pope in their group. They called him the Pope because he's infallible. Whatever he says turns out to be true. And then there was the Cardinal, Rossetti, and there was the Basilisk, who was Segre, and the young boy was Amaldi, and Majorana was the Grand Inquisitor. So they were kind of working very hard as physicists. They were kind of climbing mountains when they could, but they were spending a lot of time together, after dinner, before, whatever. They wrote a paper. The first paper that they published was written in the house of the Amaldis until midnight. And they were just being there and writing this paper. So their system of work was very, very hard. They just did nothing else but working. But they also, had a very good, nice group. Number 2. Okay, so all 3 of these, Fermi, Amaldi, and Segre, were spending their summers in various parts of the world, mostly in the US. Fermi was teaching theoretical physics in some of the summer schools, and for a long time. But then, when 1938 came, they started moving into the US because of the laws in Mussolini's time that they didn't like. In Rome, they started working with neutrons, bombarding various targets, and discovered that they could induce radioactivity of the materials that they were bombarding, and that was the Nobel Prize that Fermi got in 1938. Then, in 1938, he was able to take his family away from Italy, where the racial laws were being implemented. It was a terrible place. His wife was Jewish, and so with the excuse of going to the Nobel Prize ceremony, they were able to get a visa, and they escaped to the US. In the US, he continued his work. And the one thing which he wanted to do is to achieve a self-sustaining chain reaction. And this, after a long time, finally on December 2, 1942, they were able to have a pile that where the reaction was self-sustaining. And this is a plaque which is in Chicago by the university sports field. Next. Okay, so first I will talk mostly about my experience working in particle physics, and most of the other people I've encountered, the Italians I've been collaborating with. Unfortunately, I didn't work long enough in Italy to be able to report some of the other fields of physics that I wasn't connected to. So anyway, Amaldi was one of the Panisperna boys, and he had expected from us to work days and nights, and expected us produce some very important results. And of course, he was the head of the division, the physics department. So he, of course, was very, very busy. But he was sure to come by every day to see where we are at. So, here is a picture of him with Segre. I met Segre, next slide, when I came to Berkeley. Before I do that, I would say that Amaldi was the only one left in Italy after 1938, and he was really very dedicated to the Italian physics in various places all over. Even if he was in Rome, he was trying to do whatever he could to get the Italians to contribute in a very fundamental way, and that's why he was one of the founders of CERN. Okay, now Segre came in 1938. He was trying to come, and he had found some new elements, including plutonium-239 and the element 43. So his work was mostly on looking and studying the elements, and was 1938 was one of the summers that he was coming here, and there is a very nice episode in his book, which he was, in order to come to the U.S., he needed to have a passport stamped for the U.S. Otherwise, he would not get a visa to come here. So he went to this gentleman who was supposed to look at his tank, and he said to me, "Yeah, I need the visa so that I can go in the United States." And the fellow said, "Oh no, it's very hard. I want to give it to you, and it's impossible. It's impossible." Then he said, "Oh, you are Segre? Ah, but you are the professor of my son." And yeah, my son says you really want a lot from them, that you're working too hard. I don't need it, right? Oh yes, I need it. And you make them work too hard. He's afraid, terrified at the idea of him giving this exam in a few months, and so. I won't give you the exam. And he said to the guy, "Okay, tell your son it's okay. It's okay. He's going to be promoted. He's going to make it. Just assume that he already passed the exams." And the guy gave him a stamp. So his book is really fantastic to read. I mean, all these episodes that are incredible, unbelievable. Anyway, at this rate, I think I'll need 2 hours to finish my presentation. So Segre was working, when I came, he was working on, he had left all the heavy elements, and he was working on trying to find the antiproton. And here is this new particle that they wanted to find. This is a Lawrence Berkeley lab. There was a new machine colliding proton and antiproton, and he was also working with Italy with Amaldi, and so they sent what happened to my? You have it. Does it work now? So he was sending nuclear emulsions were irradiated with antiprotons. Turns out that the Rome group was the first one to see a proton-antiproton collision here, because a lot of energy gets released, and then you see a lot of particles. However, there is a controversy there. They couldn't publish this thing before the group at Berkeley found the antiproton, and here is Segre with his collaborators. So 3 of these got a Nobel Prize in 1956 in physics. So that was a very important point for them. So I'm going to go to the next one. Now, in 1960, we moved to the US. I came in the summer of 1961 and started working in the emulsion group because that's what I was doing in Rome. But very soon I was taken away from there and I went to work with Louis Alvarez, very exciting place to be. He was just like the guys we were talking about, Segre, Fermi, Amaldi, and he had a lot of ideas and was doing a lot of things and was very, talking to him was just, you know, for me, like being again in Rome, in La Sapienza, was very, very exciting being in a group. And he had invented a new, the idea actually of this bubble chamber was someone else, but he made it really as a very good detector. And you can see the particles coming in here. This is a proton-antiproton and lambda-lambda bar. You see an antiproton again here. And here you have two V's kind of things, which would be the lambda bar. So it was very easy to see visually what was happening when there was an interaction of particles on proton, antiproton, or whatever. So they found a lot of particles. The first one was called Xi0. Can we see the next slide? So you see this is the number of particles we've seen between 1898 and 64. We started with the electrons, and then we have the protons, the neutrons, and so on. The kappa, the K at 1950. And then all these other particles, some of them, like the Xi0 was the first one that the Alvarez group saw. Most of these, except the omega, I think, the omega minus were seen at Berkeley. So there was an incredible people who were working late at night. They went home for dinner at 6. They were back there at 8. And it was a very, very intense atmosphere. And everyone was contributing, and was really a very good place to be. So let's look at the next one. Oh, yes, I want to point out that Fermi himself, after the war and all his work for his country, he went back to do basic physics, and it was the first one to find what we call a resonance. I will explain in a minute what it is. But Fermi had gone back to work into fundamental physics. I forget about all the rest. And we go. Oh yes, and there is this other thing which is interesting, that when he found out that there were all these particles around, apparently talking to one of his students, Leon Lederman, who then also got a Nobel Prize, he said, "Young man, if I could remember the names of all these particles, I would have been a botanist." Anyway, all right, resonances. So what are resonances? What happens is that particles like the lambda and Xi0, for example, have a long life. As I showed before, the lambda was displaced. You could see that it did go a long way before it decayed into particles. And it's a lifetime of 10 to the minus 10 seconds. But some of the other particles, instead, they decay with after 10 to the minus 23 seconds. And so how do we detect these ones? We detect them as peaks, like bumps like this in distribution. So this is the kinetic energy here. And so that's why these are called resonances. And this is one example. So it's, that's a way to discover some of these particles which were not known at the time. So what happens is that in the 72, in the bubble chamber, there were about 18 particles which were found. In addition to the ones that existed before, there was about 18. And then I will talk about the Quark model shortly, but Louis Alvarez got his Nobel Prize for in contribution to particle physics with the development of the hydrogen bubble chamber and that analysis, also because at that time they started having to use computers and so on. And there were really no computers at the beginning. When I arrived here, there was one IBM small computer with the cards that had to be written, typed, and put it in, and the card readers that were jamming up. Anyway, it was now very hard. But in this group, there were 25 physicists and 25 computer scientists, which they were not called computer science at the time. But anyway, it was was a very, and then there were about 150 people upstairs, so the whole entire floor of the building. They were looking at bubble chamber pictures. I showed you one. So it was 300 people, I guess, working around them, plus the engineers and so on. Okay, so anyway, we went to the Nobel Prize ceremony with him, and it was a fantastic week that we spent in Stockholm. Although it was the winter, so there were only 3 hours of light. But we had, you know, really good time there. Okay, so next. All right. So all these particles needed to be understood. So what are all these particles, and what does, you know, what do we know about it? How do we explain all of this? So this is what's called the quark model. If you go and look at, for example, here, you know, the elements that we see in nature, you have an atom which is made by a proton here and electrons, or protons and neutrons, and so on. It's a way to explain all the table of elements. There are a lot of them. Now, can we explain the particle, many particles we have found in some similar way? So there were some ideas. Gell-Mann in 1961 came out by saying there must be some building blocks of all these particles that we see, the lambdas, the xi's, the Y stars, and so on, the K stars. There has to be some building blocks, just an analogy with what you have from the atoms. And they came out with the idea that there were some small components called quarks, U, D, and S, were the ones that are the particles we just talked, and these were not C, B, and T were not known at the time, but they started out with these three. And most of the particles that were seen in the average bubble chamber and elsewhere could be classified, saying that the constituents were these guys here, and that there was a force between which kept them together, which was called the gluon, like the glue, right? The gluon, and so we really started working on this. And the Nobel Prize again was given to Gell-Mann and Neyman in 1961 for having proposed this model. And all the particles you see, you could have a kind of things like this. There were 8 in this one, 8, and most of them could be put in some kind of design, you know, like this. Well, the other 3 quarks, C, T, and B and T, were discovered later, SLAC in 1976. And then at the same time, and also a Brookhaven by Ting et al. The bottom was discovered at Fermilab by Lederman, and then all of these, Richter, Ting, and Lederman got a Nobel Prize for this. And the top was discovered in 1995. No Nobel Prizes for the top, essentially because there were too many people involved, and they decided not to give it. And we go to the next slide. Okay, so this is discovered at CHARM. At SLAC, there was an E plus and minus machine, and I think this is all part of what my friend here is going to be talking about, all these machines. And there was a resonance scene, as we saw before, what resonance are. The particles, something, you know, that doesn't, it's very narrow because they don't leave very much, particles which are made and produced, and they decay the other way. Now, High was involved also in this thing because there was also at the same time found one tau lepton. The leptons, the electrons, we'll see later, there will be the electrons, the muons, the neutrinos, and so on. And the tau lepton was discovered in that same machine where the CHARM quark was discovered. And we joined at that point, my group joined at that point, and we found another one here, which is the one that threshold for particles with CHARM were produced. So let's go on the next one. And the top quark was the last one. Now, see, the top quark was discovered in 1995. So a long time after the CERN work. And so it was the last one, and lots of studies, lots of work done all over the place. So I was working at SLAC at the time, and then I said, well, where can, go in a place where we can find the top? SLAC, the energy is not high enough, maybe I'll go to Fermilab. So I went to Fermilab. At the same time, the detectors became huge. You look at this thing here. It was probably 8 meters or something. And there was a big group of Italians, Frascati, Bologna, Padova, and Pisa, and 13% of the collaboration, which had something like 600 people. So for the first time, I went from papers with 3 authors when I was working in the Alvarez group. Then at SLAC, we had papers with maybe 15 people. Then I go to Fermilab, and the papers had 500 people. It's just that the things became so complex, and the detectors had to be, built and taken care of. There were lots of pieces here that had to work. So what happens is that, you have engineers and physicists working together to get to a point where you can see the particle you want to see. And anyway, this is very big here. And here is the first top events. This is what we published, and it was very exciting, of course. And this plot is mine. Okay, so let's go on the next one. So, all right, so now we have filled in all of the particles that we needed, which is 6, and something else is missing. What's missing is some particles like the W and the Z, which are force particles. They are the ones which generate the force to put together all of all these particles. So we'll see something later on. And now here comes in Carlo Rubbia. He was working at Fermilab, and he wanted to do an experiment there, which would find these particles. So what happens, Carlo goes into the director and says, well, I really need to have an anti-proton-proton collider. You are working on a proton-proton one, but I want to find these particles. And of course, the Fermilab could not change all their programs to go along with this, right? So he went to CERN, did the same discussion to the director of CERN, and say, I want to do this, this, and that. Then CERN did not have a Nobel Prize at the time. So they said, well, if he's right, maybe he'll get the Nobel Prize. So all right. So gave him everything he wanted. And in a matter of a couple of years, I think, he was able to discover these new particles, the W and Z. And here is, Segre took this picture of the two of us, not Berkeley. So Segre was really taking pictures of everyone. I have some beautiful pictures from him, but this is one of them. Okay, so anyway, this is the discovery of the Z and the W, and they took, at the end of the experiment, at the beginning, they had very few events. And so you can, the W decays into quarks, and also the Z decay into particles which have quarks into them, and so on. Okay, so we can go to the next one. Number 14? Okay, so that's, no, yeah, okay, we go here and then we go forward. All right, so then let's go to the next one and then we come back. So anyway, since we have been talking about the quarks, which are shown here, the leptons, which are shown here, then the gamma and the glue and the gluino were the ones which kept together the U and the quarks, and then the Z and the W were the forces. All of these were the force particles, and this instead were the matter particles. And so how all this happens, and this is what happens, came out to the Higgs mechanism, which essentially is this thing here, which generate all the masses necessary for the W and the Z. And this was put forth in 1964, okay? 1964. Now, this is another episode that I remember like it was today. There was a conference, Salam, who was in Trieste, had set up a conference to see can we figure out what's the Higgs and how this can be discovered in order to understand all of this. And so he had a conference in 1987. I was an author in a couple of papers on Higgs searches, and so they invited me. So I went there, mostly directors of laboratories who were trying to figure out in what direction they should go. And the Letterman, who was at the time the director of Fermilab, was saying, oh, the theorists in Fermilab, they say that at the Tevatron we can discover the Higgs. And they were, had a big program on the Tevatron. And so I had just joined CDF. This was in 1986. And he said, he took me and said, Lina, now, okay, my theorists say this, but don't believe them. You're an experimentalist, so you should your job now is to find this whether the Higgs can be discovered at Fermilab. It turns out that it wasn't because the luminosity, the machines were not strong enough, and so that did not happen. So I went to, we go back one. So I went to CERN to work at that point, and a machine. There was a group at Berkeley who was working in there, so when I left Fermilab, I went to work at CERN, and here it was discovered in 2012. So you see how long it happened before the idea that this particle was going to, explain everything, and the time that it was found. So can you imagine all these years trying to find something. And that's why, it was days and nights, everyone working and moving toward the target. Can we find this particle? And eventually it was found in 2012. And the meeting I was talking about was in 1986. So long time. Okay, so here is one Higgs goes to gamma gamma. And you see that the two protons, the machine at CERN is a proton-proton. The two protons meet, and something happens, and here are the gamma-gamma. And then you have the distribution, so you see a little thing in here, but this is still significant here. Then you have the ZZ, and you see some events here. And then you have the WW. I worked on this particular channel, WW. You see that we were supposed to see this blue that you see there. So it's not very much, and here it looks also very small. But if you add together all the answers, you find out that the significance of these peaks is of the order of 5 standard deviation. Standard deviation means if you measure 10 events and you may put the error on that, and you say 5 times the size of the error, which is very low probability. So this was the Higgs discovery. And at this time, you see where the little people are. Here are the people. The detectors have become bigger and bigger and bigger because you have to look at tinier and tinier things. And so there are 2 people right here, if you can see. This is 45 meters. That's a huge detector. Okay, so can we go back on? Maybe I'm talking too much. It's okay. It's okay? 5 minutes? All right, so then I'll have to go very fast. Okay, I will. This is now this is the things we've been working about. All of these particles we've been talking about is the matter that we see, and it's only 4.6% of the universe. There are other things like dark matter, 23%, and the dark energy is at 72%. So all this work and all we know, understand, not completely, but mostly understand what happens in this 4% here, right there. The existence of this like dark matter and dark energy are proved by the astrophysicists who are looking at the entire universe, and they find that there has to be something which operates on the here is the dark matter operates on bodies in the universe. There is the galaxies. Some part of the galaxies cannot be seen because they don't reflect light, and that's what's called dark matter. It's something which doesn't reflect light, but is there because you can see that the gravity moves, influences all the galaxies around. And then there is dark energy. With dark energy is something which makes the universe expand, keeps expanding the universe, and this is probably due to some force, which is called the dark energy. So maybe we can go to the next slide. So there is a lot of work in trying to figure out what those are, dark matter and dark energy. The last other thing that is still is the gravitational waves. Einstein and his theory had predicted that there is this phenomenon when in space there is something which, some kind of cataclysmic event happens, and there's something like this ripples here happens. Like think if you're throwing a piece of a pebble on the water, you know, on the sea, you see all this, and so here are what they call gravitational waves. And this also is a big story. It includes our professor Amaldi and a group of Rome, and actually Guido Bizzella was a very good friend of us, I think, because he was 1 year before us, before me, and I was a year before you, right, at La Sapienza. So anyway, and Amaldi, of course, so I followed up their work here, and they started working on this for many, in 1970, when a hint, something Princeton or someone, Weber and Princeton thought he would have seen one of these gravitational waves. But they, you know, they were not, but this prompted the people of the La Sapienza to just get on. And Amaldi was in favor, and he worked very hard on this the last few years before he died. He actually they set up an Amaldi conference, a conference called Amaldi is still being held today. There have been 12 since 1994 when it was the first one. So it's another contribution, very important contribution from La Sapienza, which is to work on things which you know, really need to be understood. And anyway, the last time I saw Amaldi Eduardo in Berkeley in 1995, he died 3 years later, 4 years later, and he was confident that eventually the technology would improve so that you could really detect these things. And if we go to the next one, there have been a couple of three actually gravitational waves which have been detected, and of course you know, produced a lot of excitement since you know, this after all these many years. Now a big group there is in Pisa, in Italy, there is one of these detectors, and it's called Virgo, and which is this very close to Pisa, and includes many European countries, France, Italy, Netherlands, Poland, and Hungary, and they are part of the collaboration. They're collaborating with the group here, the LIGO group here in the US, which includes also many people. And so they have been participating in the results of this three which have been announced. And so it's another place where, you know, the Fermi, Amaldi, Segre, just a good look forward, you look at what needs to be understood, let's go and do it. You know, it's just trying to just take on all of the more difficult problems around, and just being happy in being able to slowly make a fast forward. And so now here is LIGO, is also this Virgo with all these Europeans involved, and they were very important because with 3 different interferometers, one in North US, one in South US, and one in Europe, you can have 3 pieces of information, so you localize where the gravitational waves came from. So anyway, the excitement I had in all this since I was, I guess I started when I was a graduate student, just, continues. There's still a lot to see and still a lot to try to find. So I'm happy, I guess, or I've been fortunate to be working with people like this. So, so thank you.